Thank you very much for the introduction. And it's my great pleasure to give a talk in this conference to celebrate the 60th birthday of Professor Maxim Kontsevich. I thank the organizers for giving me this opportunity. I first encountered mathematics of Professor Kontsevich in the mid-1990s. The first one was about Gromov-Witten invariance, and I was really impressed with his exciting and beautiful ideas. And then I looked into his other works, and I was really shocked by how each of his works completely changed each research field. And since then, I have just one of his big fans. So anyway, I'm very happy to be here. So in this talk, we shall discuss ongoing investigations of about some applications of non-Abelian Hodge theory to the study of holonomic D modules, inspired by Professor Kontsevich. And my talk consists of 3 parts. In the first part, we shall discuss a generalization of Barannikov-Kontsevich theorem to the non-algebraic setting. And in the second part, we shall discuss the irregular Hodge theory and its application to the rigidity of holonomic D modules. And in the third part, we shall discuss an application of Lagrangian cycles to the study of boundedness of some class of holonomic D modules. Okay, so let me begin with a generalization of Barannikov-Kontsevich theorems. So let X be a complex manifold with a holomorphic function f, and we assume the set of the critical points is compact. And let omega xk denote the sheaf of holomorphic k forms on X. And we have the exterior derivatives, and we also have a morphism df from omega xk to omega xk plus 1. And they are graded commutative. So it is difficult to control this one. So, and for let lambda be just a variable, and we consider the sheaf of formal power series with omega xk coefficients. And then, together with the differential given by lambda d plus df, we obtain a complex which is called the twisted Rham complex, and its cohomology group is called the twisted Rham cohomology group. And it is naturally a module over the ring of formal power series of lambda. And there are several versions of twisted Rham cohomology groups. For example, if X and F are algebraic, then we can consider the sheaf of polynomials of algebraic k-form coefficients, and we can obtain the algebraic version of twisted Rham complex and its cohomology groups. Then it is a basic question to ask: this twisted Rham cohomology group is free of finite rank over the ring of formal power series. And there are several things which we can easily observe. For example, the dimension of the cohomology group of this complex omega x dot with df is finite, because the cohomological support of this complex omega x dot df is compact, which follows from the assumption of the compactness of the set of the critical values, critical coordinates of f. And we consider the decreasing filtration by a subcomplexes given by the multiplication of lambda j's. And then the j's associated graded complex is naturally isomorphic to the complex omega x dot df. So the E1 type of the spectral sequence is given in this way. Then it is we can easily observe the twisted Rham cohomology group is finitely generated over the ring of formal power series. And we can also observe the previous question is equivalent to ask the E1 degeneration of this spectral sequence. And and there are 2 classical related results. One is given in the Hodge theory. So if x is projective and the function is 0, then we can obtain the E1 degeneration from the Hodge decomposition as observed by Doreen. And more strongly, in this case, we can obtain the isomorphism of this isomorphism for the polynomial version of the twisted Rham cohomology groups. And another is given by given just similarity theories. So if the set of critical points is just one point, then we can easily obtain the even degeneration for the trivial reasons. I mean, in this case, the L cohomology group of this complex is 0 unless L equals the dimension of X. So we can obtain the even degeneration for trivial reasons. And let me remark, in this case, we can obtain this isomorphism for the formal version of the twisted Rham cohomology groups. But in general, we don't have the isomorphism of the polynomial version of the twisted Rham cohomology groups. And this even degeneration or its generalization are very fundamental in the Hodge theories. And for instance, they are useful to obtain some vanishing theorems. And this even degeneration in the seniority theory is also very important. For example, it is a starting point of the deep theory of Kyoto Saito and Mochizuki Saito about primitive forms. So anyway, this question is related with some deep theories of mathematics. And the modern study in this direction was opened by the celebrated theorem of Barannikov and Kontsevich. So they established the even degeneration in the case X is algebraic and the morphism F is projective from X to C. And more strongly, they obtained the isomorphism for the polynomial version of twisted Rham cohomology groups. And so this is important, for example, in the study of holonomic random model in the mirror symmetry. For instance, it is essential in the proof of the smoothness of some moduli space associated with holonomic random models. And as far as I know, the proof of the original proof of Barannikov and Kontsevich is a generalization of the method of Doremi and Illusi to obtain the even degeneration in the case F equals 0 by using the mod P reductions. And the alternative proof was given by Saba by using the micro-localization and the Hodge modules. And it was another alternative proof was given by August and Borowski by using non-Abelian Hodge correspondence over finite fields. And there are many variations of the theorems. For example, if X and F are algebraic, but F is non-projective. And in this case, we have to impose some non-degeneracy condition to the behavior of F at the infinities. And for example, Saba established the even degeneration in the case F is a cohomologically tame. It is a kind of non-degeneracy condition at the infinities. And the L2 Hodge theory for X and pair has been also developed by some people. And in particular, Lee and Wen studied the case X has a complete scalar metric with bounded curvature, and F is strongly elliptic. So, strongly elliptic means a kind of degeneration condition at the infinities. And in this case, they obtained the even degenerations. And let me remark, in these studies, some conditions are imposed on the behavior of X and F around the infinities. For example, the algebraicity or completeness of scalar metrics for X, or some non-degenerate conditions, cohomologically tame or strongly elliptic for F. So in these studies, some assumption is imposed on the behavior of X and F around the infinities. So we shall return to this point later. And here, let me remind you, the theory of twisted D modules has been developed by Saba and myself as a twisted version of Hodge modules due to Saito, based on the idea of Simpson meta-theorems. And it is a branch of the so-called non-Abelian Hodge theories. And in this first part of my talk, I'd like to explain two things. First, the theory of mixed twisted D module is a natural framework to study the algebraic twisted Rham complex. And second, we can also use it to study the non-algebraic case. So I'd like to explain two things in the first part of my talk. So anyway, so let me briefly review what is a twisted D module very briefly. So let Rx denote the sheaf of associative algebras of C lambda times X, which is obtained as the canonical quantization of the symmetric tensor product of the tangent sheaf with respect to the natural symplectic structure of the cotangent bundle. More explicitly, let d C lambda times X denotes the sheaf of holomorphic linear differential operators, and let Rx denotes the sheaf of subalgebras generated by lambda times the pullback of tangent sheaf to C lambda times X. So for example, if X is an open subset of Cn, Rx is generated by lambda times del Zi. And the operators lambda del Zp and the coordinate X, Zq satisfies these commutation relations. So, this is Rx is natural quantization of the symmetric tensor product of tangent bundles, tangent sheaves. And in this talk, we consider only left Rx modules. So, an Rx module is equivalent to O module on C lambda times X equipped with a meromorphic family of integrable connections like this one. I mean, so we have we allow the pole of order 1 at lambda equals 0. So so if O module is equipped with this kind of family of integrable connections, it gives Rx modules. So for example, for any holomorphic function f on x, we can consider the family of integrable connection, meromorphic family of the integrable connection d plus lambda inverse df. This is a family of the integrable connections for the structure sheaf. So this gives Rx module denoted by LF. And then a mixed twisted D module on X is defined to be an Rx module M with some additional data satisfying some conditions. And I'm sorry, it does not make sense, but I'd like to avoid to explain the precise definitions. But let me say one of the important conditions is the Rx modules are flat over OC lambda. So if X is a point, then a mixed twisted D module is locally free OC lambda module of finite rank. So I don't explain the precise definitions, but one of the important conditions is flatness over C lambdas. So if X is a point, then twisted D module automatically satisfies the locally free OC lambda modules of finite ranks. And one of the basic results in the theory of mixed twisted D module is an enhancement of functors for algebraic conic D modules by twistor structures. I mean, there are standard functors for algebraic conic D modules like push forward, pull back, and tensor product, inner homofis, and duality, and something. And there are canonical enhancement of these functors acting on the derived category of algebraic mixed twisted D modules. For example, we got the direct image functor in the level of R modules more explicitly in the case if it's a projection of y times z to y, assuming z is projective. And in this case, we consider omega z to the j, which is a pullback of the lambda minus j times the pullback of omega z j on c lambda times y times z. And it is equipped with the differential induced by the exterior derivative of z. And then from an Rx module M, we can consider the Rham complex. I mean, these derivatives and the family of meromorphic family of integrable connections of M induces a complex of scenes M tensor omega to the z dot on c lambda times y times z. So by taking the push forward to c lambda times y, and taking the cohomology shifts, we obtain the Ry modules, R modules on y in this way. And if M underlies a mixed twisted D module on X, then each Ry module, these guys are mixed twisted D modules on Y. So in this sense, the push forward for holonomic D modules is enhanced to mixed twisted D modules, the push direct image for mixed twisted D modules. Then, as I mentioned, the theory of mixed twisted D module is a natural framework to study algebraic twisted drum complexes. For example, let F be a morphism, projective morphism from X to C, as in the case of Barannikov-Kontsevich theorem. Then we can extend it to a projective morphism of smooth projective varieties from X bar to P1, such that the inverse image of infinity is normal crossing. And then, as in the case of holonomic functions, we can consider the Rx bar module by considering the family of meromorphic integral connections D plus lambda inverse GF. And we can show this underlies the mixed twisted D module on X bar. And the drum complex of this Rx bar module is naturally isomorphic to the complex analytic version of twisted drum complex. So let Ax bar denote the morphism collapsing X bar to a point. Then, by the punctuality of mixed twisted D module, these OC lambda modules, these modules are underlying mixed twisted D module on a point. And it means these guys are locally free OC lambda modules. And we can observe this implies, this locally freeness implies the Barannikov-Kontsevich theorems. So in the algebraic case, we can apply the theory of mixed twisted D modules in a rather straightforward way. Then we ask what happened in the non-algebraic case. And so actually, so we are assuming X is scalar, and we ask the E1 degeneration whether the E1 degeneration holds or not in this case. And actually, this was asked by Professor Kontsevich to me several years ago, if I understood it correctly.
Yeah, my question is, if it's X scalar only in the neighborhood of critical locus?
Yeah, it's in the case, yes, yeah. Yeah, so assuming scalar on the neighborhood of critical locus, yes. And yeah, and so I'm not sure if it was a serious question or not, but let me report the answer is yes. And we have, let me mention two main issues to study these questions. First, we need a new argument. I mean, as I mentioned in the previous studies, twisted drum complex, in the previous studies of twisted drum complexes, we need some conditions on the behavior of ambient space X and the function F around the infinities. And in the isolated singularity case, it was exceptional. We don't need such conditions. But in that case, the E1 degeneration is trivially correct. So, to study the general case, we need a new argument so that the behavior, we can ignore the behavior of X and F around infinity. And another issue is related with a refinement of the theory of mixed twisted D modules. We need to show mixed twisted D module is preserved by the direct image of a non-algebraic morphism under some appropriate conditions. So let me begin with the issue 2. And so regarding the issue 2, we proved regular mixed twisted D modules are preserved by a morphism from a scalar manifold to a complex manifold Y, assuming the support of the mixed twisted D module is proper over Y. Yeah, proper over Y. And and here the regular means the underlying holonomic D modules are regular singulars. And I don't think this regularity is necessary for this generalization. But at this moment, I have studied only the regular case. And for this theorem, an important key step is the generalization of Kashiwara-Kawai theorems. it briefly says, so there are two complexes, so it means there exists the quasi-isomorphism between the Drum complexes of pure-twisted D modules and L2 drum complex associated with the smooth part of the pure-twisted D modules on C lambda times Z. Sorry. So let me remind you, there is a very famous theorem of Kattanika-Schmidt and Kashiwara-Kawai, which says about the comparison of intersection complex and the L2 complex associated with various polarized variation of Hodge structures. And it roughly says there exists a comparison of these two complexes on C lambda star times X, I mean outside of lambda equals 0, in the case of Hodge modules, pure Hodge modules. And Kashiwara and Kawai also announced a theorem saying this quasi-isomorphism extends to a quasi-isomorphism on C lambda times X. And so this is a generalization of the theorem to the case of tame harmonic bundles. So anyway, so we need some, this complex is, this complex of, so drum complex of twisted D module is very closely related with the theory of twisted D modules, and the L2 complex is adapted with harmonic theories. So this comparison theory is very important in the generalization of twisted D modules to the context of non-algebraic context. So anyway, so we obtain this kind of generalized Kashiwara-Kawai theorem, and we can, by using this theorem, we can obtain this refinement of the functoriality of the direct image of mixed twisted D modules. And then let me explain a brief outline of the study of the issue 1. So let me remind you, so X is a Kähler manifold with a holomorphic function f such that the critical value, the critical locus is compact. I mean, so we assume only the neighborhood of the set of critical points is Kähler. And we can assume the set of critical points is connected and the critical value is 0. And we have the by considering the family of integral group connection d plus lambda plus df, we obtain the mixed twisted D modules. And so, and let pi 0 denotes the projection of C lambda times y to C lambda for any complex manifold y. Then, as I mentioned, the drum complex of LF is naturally isomorphic to the twisted drum complex. So we like to prove this guy is free over the ring of formal power series. And let me remark, so so the support of LF is not compact, not proper over, not compact. So we cannot apply the previous theorem directly to this guy. So first we replace this complex to some other complexes. So let iota f denote the graph embedding, and we have the so then the push forward of the structure sheaf, we obtain the mixed twisted D module M. And by considering, we also have the twisted D module LT corresponding to the function T on x times C lambda, x times Ct. Then you can easily observe the direct image of LT by iota f is isomorphic to the tensor product of M and LT. And the drum complex of the push forward of the drum complex of LF is isomorphic, quasi-isomorphic to the drum complex of M tensor L1 shifted up to the shift of the degree. So we'd like to prove these guys are free over the ring of formal power series. And then so there is a brief iteration of V of M along T equals 0. And then it is standard to replace this complex by this complex, total complex. I mean, there exists a morphism del T plus lambda inverse from V minus 1 m to V0, lambda inverse V0 m. And by considering the Rham complex in the x direction, we obtain double complex. And let C1 dot denotes the total complex of this double complex. Then this guy is quasi-isomorphic to this complex. So we want to prove these guys are free over the module over these guys are free over the module of free over the ring of formal power series. And here let me we introduce one scaling parameter u, and we consider the complex of series in a bigger space. So I mean, so let pi 0, 1, 2 denotes the projection of c lambda times x times ct times cu to c lambda times x times ct, and pi 0, 3 denotes the projection of this space to c lambda times cu. Then we consider the pullback of these guys to c lambda times x times ct times cu, and we replace del T plus lambda inverse by u del T plus lambda inverse. And then the restriction and the total complex is denoted by C dot. And then the restriction of this complex to u equal 1 is equal to the previous the complex C1 dot. So we want to prove these guys are free over the ring of formal power series. And but first, so we like to study the restriction of u equal 1 and the formal neighborhood of lambda equals 0. But first, we study the restriction to u equals 0. And for this guy, we can apply the theory of mixed twisted modules, and we can show these guys are free. I mean, so we like to prove these guys are locally free, and it follows from as follows. So this complex is quasi-isomorphic to the Rham complex of the quotient of V0 by V minus 1. And then at group V, each group V C M underlie mixed twisted modules. And for the direct support, whose supports are contained in the compact set which follows from the assumption of the compactness of the critical points. And so by applying the theory of mixed twisted modules, these guys are locally free Cauchy-Lambda modules. And then by standard technique, we can show these guys are free Cauchy-Lambda, locally free Cauchy-Lambda modules. So here, so we use the theory of mixed twisted modules. And then the following are the standard techniques. I mean, and then we can we study the restriction to the formal neighborhood of u equals 0, and it is not difficult to show that these guys are free outside of lambda equals 0 by using the standard theory of D modules, and then together with the locally freeness of these guys, we can show this is free across lambda even at lambda equals 0. And as a result, so the restriction to the formal neighborhood of u equals lambda equals 0 are free. So first we study here, and then we study formal completion here of u equals 0 here, and then we obtain the freeness of the formal completion at 0, 0. And then from the different directions, first we can show the restriction to lambda equals 0 is coherent from the assumptions. And then it is standard to obtain the restriction to the formal neighborhood of lambda equals 0 are coherent. And then, so because this is free, so we can show the restriction to the neighborhood of 0, 0 is free. And then by using the shift action, we can show the restriction to lambda equals 0 is free. And then by considering the restriction to u equals 1, we can obtain the, the desired freeness. I mean, so this is an outline to obtain a non-algebraic generalization of Barannikov-Kontsevich theorems. And so in this argument, it is essential to use the additional rescaling parameter u, and it also appeared in the irregular Hodge theory, which we shall discuss in the next. Okay, so so let me remind you a very interesting generalization of Barannikov-Kontsevich theorem about the cohomology of Kontsevich complexes. So let F be a projective morphism of algebraic manifolds from X to C, as in the case of Barannikov-Kontsevich theorems, and it extends to a projective morphism from X bar to P1, such that the inverse image of infinity is normal crossing. And then we have the morphism from df from the sheaf of logarithmic J forms to the sheaf of meromorphic J plus 1 forms. And the sheaf of meromorphic J plus 1 form contains the sheaf of logarithmic J plus 1 forms. So as the inverse image of logarithmic, the inverse image of the sheaf of logarithmic J plus 1 forms, we obtain some subsheaf of omega jf of omega jx log h. And so, and for any complex numbers lambda and tau, we obtain the differential lambda d plus tau dx, and together with this complex, we obtain a complex which is called the Kontsevich complex. And then it was proved the dimension of the cohomology group of this complex are independent of the complex numbers lambda and tau, which was first proved by Professor Kontsevich. In the case, the pole divisor F inverse infinity, F star infinity is reduced, and the general case was established by NO and Saba and U. And the tau equals 0 case was also established by Saito, Moriko Saito. And let me remark, the specialization of this theorem to tau equals 1 is equivalent to Barannikov-Kontsevich theorem. And the parameter u in the previous page is equal to tau inverse. And let me also remark, this theorem, we can also prove this theorem by relating the family of Kontsevich complexes to the relative drum complex of the V filtration of mixed twistality module given by as L tau f, I mean, corresponding to the function tau f of C tau times x. And the study of Kontsevich complexes stimulated the study of irregular Hodge filtrations. The idea of irregular Hodge filtrations was originally introduced by Dorin. He introduced a quasi-isomorphic subcomplex of the meromorphic twisted drum complex in the one-dimensional case. And he proved and he also introduced a filtration on this subcomplex. And he proved the E1 degeneration of the spectral sequence. So in particular, we obtain a filtration of this twisted drum cohomology group, and which it is called the irregular Hodge filtrations. And Saba and Yu studied generalization independently in the different directions. And so when we are given a morphism f from x to c, which is projective, as in the case of Barannikov-Kontsevich theorem, for simplicity, you introduce a quasi-isomorphic subcomplex of this complex with a filtration, and the generalization of the work of Dorin. And it is quasi-isomorphic to the Kontsevich complex omega f dot with d plus df with the stupid filtrations. And NO and Saba and U proved the E1 degeneration of the associated spectral sequence, and it is equivalent to the equality of, in the case, lambda equals tau equals 1 and lambda equals tau equals 0, 0. So actually, this is the first interesting question in the study of irregular Hodge filtrations as far as I know. And then after the works of Saba and Yu and later myself, irregular Hodge filtrations are formulated as something attached with rescalable integral mixed twistor D modules. And it turns out rescalable objects or rescalable integral mixed twistor D modules are equivalent to exponential mixed Hodge modules. And we can apply this equivalence to the study of rigidity of holonomic D modules. So let me explain it. So let me briefly explain what is integral mixed twistor D modules and rescalable objects. And we consider only algebraic case. So so we consider the sheaf of algebraic functions on the C lambda times x with Zariski topology. And we also consider the sheaf of algebraic linear differential operators on C lambda times x. And so let algebraic R to the x denote the sheaf of subalgebras in the sheaf of algebraic linear differential operators on C lambda times x generated by lambda times the sheaf of vector fields on C lambda times x, which are logarithmic along lambda equals 0. So, for example, if x is an open subset of Cn, then the algebraic twisted algebraic R to the x module is generated by lambda del d1 to lambda del dn and lambda squared del lambda. So we add one more operator. And then, as in the case of Rx modules, we consider only direct algebraic R to the x modules. So algebraic R to the x module is equivalent to an O module on C lambda times x with meromorphic integral connection like this one. It allows a singularity and at lambda equals like this one. And so, for example, for any algebraic function f on x, we obtain the so we have the this integrable meromorphic connection d plus d lambda inverse x. So by this meromorphic integral connection, we obtain an algebraic R to the x module. And an algebraic integral mixed twistor D module on x is defined to be an algebraic R to the x module with some additional data satisfying some conditions. So again, this does not make sense, but I like to avoid the precise definitions. But, so anyway, so we essentially we like to consider algebraic R to the x module satisfying some nice conditions. And then the scalability is defined as follows. So we consider a morphism C lambda from C lambda times C tau star times x to C lambda times x given by the multiplication of lambda and tau to lambda tau inverse. And from an algebraic R to the x module M, we obtain algebraic C tau star times x module as a pullback on C lambda times C tau star times x. And it is naturally C star equivalent with respect to the natural C star action on the space C lambda times C tau star times x. And this module is called rescalable if the pullback phi star M is an algebraic integrable mixed twistor D module on C lambda star times x. So this is non-trivial condition because the role of tau is the parameter in the space directions and lambda is twistor parameters. And this morphism mixes the twistor parameter and the parameter in the space directions. So this control is quite non-trivial conditions. And usually this is not satisfied. But if it is satisfied, algebraic integral mixed twistor D module is called mixed algebraic. It's called rescalable. And then the irregular Hodge filtration is defined in terms of V filtration of rescalable objects. I mean, so if an integral mixed twisted image is rescalable, there exists a V filtration of this pullback phi star m along tau equals 0. And the identification of each VA phi star m is coherent pi star Rx algebraic modules. So, and we also obtained by taking the restriction to lambda equals tau, we obtain C star equivalent coherent Rx modules. And then there exists a good filtration on the D module, CDR. So we have the underlying D module of M by taking lambda equals 0. And there exists a good filtration on this underlying D module such that this induces this guy by these constructions. So in this, and by varying A, we obtain R indexed filtrations, and this is the irregular Hodge filtrations. And so by using this formulation, we can consider some very nice functional property of irregular Hodge filtrations. But anyway, so and then we can show algebraic rescalable integral mixed twisted D modules and exponential mixed Hodge modules. We can obtain the equivalence of algebraic rescalable integral mixed T modules and rescalable exponential mixed Hodge modules, which I'd like to explain in the next. So exponential mixed Hodge modules is a straightforward generalization of exponential mixed Hodge structure introduced by Kontsevich and Soibelman. So let me explain it very briefly. So algebraic mixed Hodge module on a complex algebraic manifold X is a good filtered regular holonomic D module MF with some additional data satisfying some conditions. And an exponential mixed Hodge module on X is an algebraic mixed Hodge module MF on CT times X. So we consider the bigger space and such that the projection, the direct image of projection of the regular holonomic D module M to X is 0 in the derived sense. And so we consider the category of exponential mixed Hodge modules, and we also consider the category of rescalable integral algebraic rescalable integral mixed twisted D modules on X. Then there exists an equivalence between the category of exponential mixed Hodge modules and rescalable integral mixed twisted D modules. I mean, it is given as follows. So we consider there exists, we have the mixed twisted D module LT on CT times X corresponding to the function T. By considering the meromorphic connection given by D plus D lambda inverse T, we obtain the algebraic integral mixed twisted D module on CT times X. And for any exponential mixed Hodge module on X, which is actually the mixed Hodge module on CT times X, so by taking the least construction, we obtain the algebraic integral mixed twisted D module on CT times X. So by taking the tensor product of these two algebraic integral mixed twisted D module on X, CT times X, and by taking the push forward to X, we obtain an integral mixed twisted D module X. And we can show this guy is rescalable, and actually this construction gives an equivalence of exponential mixed Hodge modules and mixed rescalable integral mixed twisted D modules. And then we'd like to apply it to the study of the rigidity of holonomic D modules. So let me remind you, the motivic D modules are the class of which is a minimal class of holonomic D modules, which is closed under extensions, subquotients, and push-forwards and pullbacks, and it containing the structure sheaf for any algebraic smooth varieties. And extended motivic exponential D modules is the minimal class of the same conditioned, but it contains OX d plus df for any algebraic smooth varieties x and algebraic functions f. So this category it is of course larger than previous ones, and this also contains irregular singular holonomic D modules.
So in the second conjecture, is X compact or could be a quasi-projective?
X is so I'd like to say in this case X is projective and H is hypersurface. So essentially quasi-projective. So the conjecture of Professor Kontsevich says if holonomic D module M satisfies x to 1 mm equals 0, I mean it means it is cohomologically rigid, or if we consider the moduli space of holonomic D module, then the tangent space, virtual tangent space is 0, and then M is actually extended motific exponential. This is a conjecture of Professor Kontsevich, and and this is a generalization of a more classical conjecture of Professor Simpson, which says so we consider regular singular meromorphic flat bundle on XH. So, XH, which means so this guy has regular singularity along the hypersurface H. And suppose this regular singular meromorphic flat bundle is irreducible and rigid, then it is motific. And of course these conjectures are too difficult for us to prove at this moment. But let me remind you, Simpson discovered, obtained some very interesting results related with his conjectures. I mean, Simpson discovered such a rigid regular singular meromorphic flat bundle underlies a polarized variation Hodge structures. And we like to we can obtain an analog of this result in the context of irregular singularities, and so we can apply it to the study of this conjecture of Professor Kontsevich. So I'd like to explain it. So let X be a smooth complex projective variety with a simple normal crossing hypersurface H, and we consider a good meromorphic flat bundle on XH. And suppose N0V denotes the kernel of the trace morphism from N0V to OX star H, and let N0V denotes the minimal extension of this meromorphic flat bundles. Then suppose we assume this meromorphic flat bundle is irreducible, and the first Rham cohomology group of this D module is 0, and the eigenvalues of alpha of the formal model of V nabla satisfies absolute values are 1. For any eigenvalues of the formal model of V nabla, the absolute value is 1. Then there exists a regular holonomic D module on Ct times X, such that M underlies a mixed Hodge module, and V is described as the push-forward direct image of M tensor Lt. Here, so pi x denotes the projection to X, and Lt denotes the holonomic D module associated with the function T. And let me remark. So if x to 1 VV equals 0, then this condition and the condition for eigenvalues of formal model are satisfied. So, and we can also impose x to 1 mm equals 0 to these guys. So in this sense, at least for this kind of V nabla, we can reduce the conjecture of Kontsevich to the classical conjecture of Simpson's. And let me remark, Sava studies the case x equals p1 by using Barannikov-Kontsevich algorithms. So in this case, yeah. So in this actually in the x equals p1 case, Sava already proved the motific property, motific exponential property for rigid meromorphic flat bundles. And let me explain an idea of the proof. So, so we can assume the determinant of V nabla is unitary. And this is always trivially satisfied if x to of V equals 0, x to 1 of V equals 0. But anyway, and there exists, so in this, anyway, so there exists an Rx module M such that M underlies a pure twisted D modules, and the underlying D module of M equals the minimal extension of V, and we can also assume the determinant of M underlies an R children modules. I mean, it also is equipped with the action of lambda squared del lambdas. And there also exists an Rx submodule N of Nm such that N underlies the pure twisted D modules, and the underlying D module of N equals the minimal extension of N0V. And in general, I mean, without the assumption for this vanishing, there exists an obstruction class in this vector space such that M underlies an Rx, M is equipped with the action of lambda squared del lambda in a compatible way with the action of Rx if and only if this obstruction class is 0. And moreover, if this obstruction class is 0, then the action of Rx lambda squared del lambda module over M are classified by this vector space. And so now we assume this vector space is 0. Then this obstruction class is trivially 0. And so because we are assuming the meromorphic band is reducible, this vector space is also 0. So this guy is also 0. So there exists a unique Rx lambda squared del lambda module structure M tilde over M. And we can prove M tilde has a unique algebraic structure which denoted by M. This way. And we can prove this guy is rescalable, integrable, mixed twisted D module on X. So by the previous equivalence, we obtain the existence of mixed Hodge module on X times Ct such that this M is induced by MF for this mixed Hodge modules. So this is actually a generalization or analog of Simpson's result on the existence of the structure of polarized bichromatic structure for rigid local systems. So we can, so by using this result, we can obtain this type of theorems. Okay, so in the final part, we shall discuss an application of the Lagrangian cycles associated with meromorphic flat bundles. So so let me remind you, for any holonomic D module M, we have the characteristic cycle, which is an effective cycle of Lagrangian cones. I mean, each lambda I is Lagrangian cone. Cone means we have the natural sheath action of the cotangent bundles, multiplication of complex numbers, and lambda I are preserved by such sheath actions. So we for any holonomic D modules, we have the characteristic cycles. And this is a useful invariant. And for example, if X is projective, the altering sum of the dimension of the cohomology group is described as the intersection number of the zero sections and these characteristic cycles. So it is very useful, but it lost much information. For example, the characteristic cycle of this holonomic D module is independent of 1. So if we consider this holonomic D module, so this guy depends on alpha, but the characteristic cycle is independent of alpha. So so it lost much information. And Professor Kontsevich proposed an idea to attach a Lagrangian cycle in the cotangent bundle of an algebraic holonomic D modules. More precisely, he introduced the idea of arithmetic support of algebraic holonomic D modules. And here, as an analog, by using mixed twisted D modules, so instead of arithmetic support, by using the theory of mixed twisted D modules, we attach a Lagrangian cycle to any algebraic holonomic D module M. I mean, there exists a Jordan-Hölder filtration on M such that the associated graded object is semi-simple. Then, according to the general theory of mixed twistor D modules, there exists a pure twistor D module M such that the underlying D module is isomorphic to this semi-simplification of M. Then, we consider the restriction of this Rx module to lambda equals 0. Then it is the module over the symmetric tensor product of tangent sheaf. So we can consider the support in the cotangent bundles. So let sigma m denotes the Lagrangian cycle on T cycles obtained as a support with the multiplicity of this module over the symmetric tensor product of the tangent sheaf. And I'd like to explain an application of these Lagrangian cycles. So let lambda I, let lambda I be Lagrangian cones on T cycles, and so we consider effective cones of effective cycle of Lagrangian cones on cotangent bundles. And then we introduce a class of holonomic D modules whose characteristic cycle is dominated by this lambda. Then we can show that this class of holonomic D module is bounded in the sense there exists a scheme of finite type over C and the family of flat family of holonomic D module MS such that MS is flat over S, and for any point of S the specialization of MP to P times X is a member of C lambda, and for any member of C lambda, there exists a point P of S such that M is isomorphic to the specialization of MP, MS to P. So, and it is essential to consider the case of meromorphic flat bundles, and so let XS be a more smooth family of a complex projective variety with a normal costing hypersubset HS. And so for any point of S, the specialization is denoted in this way. And we consider the class of meromorphic flat bundles V nabla of rank R such that which is a family which is a meromorphic flat bundle XP on XP for some P such that its irregularity is dominated in this way. Then we can show this class of meromorphic flat bundle is bounded. And this was asked by Eno and Langer, and Hu and Tessier proved studied this problem, and they proved the boundedness of the dimension of the Rham cohomology group of the family of this kind of family is the case dimension of X equals 2. And they also obtained many interesting consequences, even in the higher dimensional case, from this boundedness in the two-dimensional case. And Saba proved the finiteness of meromorphic flat bundles on P1H, I mean the case X equals P1, such that V nabla is contained in this family, and V nabla is cohomologically rigid, and the eigenvalues alpha of the formal monotony of V nabla are nth roots of 1 by using Barannikov-Kontsevich algorithms. And let me explain just some ideas for the proof. So we'd like to consider the resolution of Lagrangian covers. I mean, let sigma denote algebraic subvariety whose dimension is equal to the dimension of X, and the projection to X is finite. And it is called Lagrangian. It's a smooth part of the sigma is Lagrangian. And so we are interested in the behavior of the Lagrangian cover around H. And I don't explain the precise definitions, but for there exists for any point of H, there exists a condition good at P. And so if this condition is not satisfied, it is called turning point of the Lagrangian covers. And I don't explain the precise conditions, but for example, if the image of the logarithmic form alpha d1 d1 is then it is good, and the image of d1 inverse is good, but the image of d1 inverse d of d1 inverse d2 is not good. Or so essentially we'd like to separate the ramification and the pole of Lagrangian covers. But anyway, so it is not usually satisfied, but we can show there exists a birational projective morphism such that the pullback of the Lagrangian cover is good. And then by using this resolution of turning points, we can prove the boundedness of prescribed bounded singularities. I mean, so if we fix good Lagrangian cover of Xh, then we consider the class of meromorphic bundles whose Lagrangian cycle is very close to the given good Lagrangian cover. Then we can show the class is bounded. We can prove this kind of claim by using standard techniques in the moduli space of vector bundles. And we consider the family of Lagrangian covers such that the degree is smaller than R, and the closure of sigma in T star X log H tensor or NH is proper over X for some fixed number N, R and N. Then it is easy to show this is bounded. This is a bounded family. So, and we can also show if meromorphic bundle satisfies the condition, some bound. The irregularity of Vn is bounded by large number n. Then its Lagrangian cycle is contained in these members, in these families. So then, so there exists a bounded family of resolutions for this bounded family of Lagrangian covers, and for each Lagrangian covers, we have a bounded family of meromorphic bundles whose Lagrangian cycle is close to the given Lagrangian cycles. So by applying these boundedness, we can obtain the desired results. So I'll stop here. So thank you very much.
Thank you very much.
Thank you very much. You really seem to solve many things which I was thinking in various parts. But there was a question also I asked if you have closed smooth Lagrangian submanifold in cotangent bundle, which is H1 is equal to 0, this should correspond to some again rigid.
Yeah. It is. Yeah, I know your conjecture is written in the Japanese journal.
Yeah.
But I'm thinking, but at this moment it's still difficult for me. Yeah.
Other question?
Can you show the slide with sigma v, the definition of sigma v? The previous two slides. So so in the next slide you say something about sigma v. What does it mean? Before this, the first proposition. What is sigma v in this first proposition?
So for meromorphic flat bundle V nabla, we can consider the associated Lagrangian cycles. So it is so if V nabla is irreducible, V nabla has pluriharmonic matrix satisfying some conditions, and we have the associated Higgs bundles, and so we have the associated spectral cover of the Higgs field, which is sigma V in this propositions.
And what does it mean congruent to sigma modulo T star X?
Yeah, of course, I didn't explain the precise definition of this, but essentially, so we like to, so G inverse, so for instance, so we don't divide this guy and this guy. I mean, how to, so if we, so image of dA, A is some meromorphic functions, and so this is this gives Lagrangian curve of degree 1, and we can also consider dA plus alpha dz 1 over g1. So if h equals g1 equals 0, and so in the study of meromorphic flat bundles, we don't have to distinguish these two Lagrangian cycles. So we regard so dA and dA plus alpha dz1 over g1 as we regard the same as the same. So in this sense, so we ignore the logarithmic or regular terms or logarithmic terms. So this is just the explanation in this particular case, but we can generalize this kind of condition to more general cases. Yeah. So I'm sorry, I didn't explain the precise definition, but.
Other question?
For the rescalable mixed twistor D module, what is the corresponding Betty data? What is the Betty data for rescalable integrable mixture?
So if we have twistor D module or rescalable integral, something like that, and yeah, so we can consider we have the underlying D module at lambda equal 1, and so by taking the drum complex, we obtain the or it's better to consider the enhanced object, which is some power stick with stock structures. So so we have. So by taking lambda equal 1 and by taking the drum factor or enhanced drum factor, we obtain some power stick or power stick with stock structures. But it might be interesting to ask, so what kind of conditions should be satisfied for it? And at this moment I don't know the answer, but so maybe this is not the answer for your question. But so anyway, so we have the underlying Betti structures of. We can consider the underlying Betti structures of twistor D modules. So usually for twistor D modules, we consider just C power sheaves. And so usually for Betti structures, people are interested in Q structures or D structure or something like that. And we can formulate some K-Betti structures for any number for any field of subfield of C, and so we can consider the Betti structure of twistor D modules, and but I think it's more interesting to consider the D structure or more general structures. But so sorry, I'm not sure. Maybe this is not the answer for your question, but we can formulate this kind of structures.
All right, let's take other questions during coffee time, and we will continue in 22 minutes with a talk by Yong. Let's thank Takuro. Thank you.